Hello, this is part 3 of the lecture on linear independence. So we are in now in the business of determining whether or not a given set of vectors is linearly independent, or on the other hand, that set may be linearly dependent. And so we last established the connection between answering or addressing independence in terms of solving a system of a homogeneous system of equations. For example, here with this set of column vectors, what we should do is to form an augmented matrix. And here you could choose to form the augmented matrix of the homogeneous system, or you can just simply work with the original matrix. Each of these vectors, this is a subset of C5. So each of those vectors contains complex numbers on C5. You could choose to work with the augmented matrix such that the last column would be a column of zeros, and then you can stack these numbers here, right? So you can say this is 2 minus 1, 3, 4, and 2 for the first column, and then you can write that column as the second column and that one as the third column, and then off you go. Once you do that, you're interested on computing the reduced row echelon form to therefore establish what is the solution set of this of a homogeneous system that contains these columns as the columns of the coefficient matrix. Once you establish what is that solution set, you may have that solution set will have either a unique solution, which will be trivial, or it would have infinitely many multiple solutions. That's the case in which there are rows of zeros on the RREF, and that will allow you to establish which of the scalars, and therefore here actually there are alpha 1, alpha 2, and alpha 3. There are 3 possible scalars, and if there is a case in which one of them is a free variable and the other are dependent variables, that would be a scenario in which you may come up with a non-trivial solution for the homogeneous system, or a non-trivial relation of linear dependence. You would classify this set as a linearly dependent set. So either the homogeneous system has the trivial solution as a unique solution. In such case, you have independence, or you have non-trivial solutions for the homogeneous system. In that case, you call the set dependent. So instead of working with the augmented matrix, we can simply work with the matrix with 3 columns. We can row reduce that matrix. In this case, as we had established here, the number of columns is 3, and the number of non-zero rows, right? The number of non-zero rows is 2. So there are there's one free variable, and in fact, what would that be? So the indices for dependent variables are 1 and 2, and the index for free variable is 3. Okay, so the last variable would be the variable you call, in this case, alpha 3 would be the the free variable, and you could express alpha 1 and alpha 2 in terms of alpha 3, but immediately we can say, this homogeneous system has infinitely many solutions, and therefore we would call the set, the original set, a linearly dependent set. So now consider this theorem, and suppose we have a matrix storing columns, the columns that define a set of vectors in Cm, and B is the RREF of this matrix. So here we realize that if we're going to say that the set, the original set, is this is going to be another direct way of ruling the classification of independence. We consider the set as being independent if and only if the number of columns is exactly equal to the number of non-zero rows in the row reduction. Okay, let's be clear here that not to confuse what we're calling here the number of columns of the coefficient matrix. This is by considering a linear system that has matrix of coefficients 0. and 0 as the vector of constants. But if instead you form the augmented matrix, this augmented matrix would have n plus 1 columns, right? So we're always calling n the number of columns in the matrix of coefficients. And if that n is exactly equal to the number of non-zero rows in the RREF, then we're going to have independence. So here we have a case. This set is a subset of, let's see, how many entries we have in a given vector. There's 2, 4, 6. So this is a subset of C6. And so we want to come up with whether or not this set with 5 vectors in C6 is dependent or independent. We form the augmented matrix and realize that in this case we have that n, so we have 5 columns there, so n equals 5, okay? And the number of non-zero rows here, R equals, the number of non-zero rows is 4. So since the number of non-zero rows is not exactly equal to the number of columns, then we would say that in that case, this set is classified as dependent. In this next example, so we have now 4 vectors, and this set of vectors is a subset of C5, right? Each of those vectors has 5 entries, and in general we're considering that those entries are complex numbers. So what we do is we form the augmented matrix and row reduce, okay? Compute the RREF of this matrix whose columns are defined by the elements of this set. And remember, so here we're starting with the number of columns equals 4, and we're finding that the number of non-zero rows in the RREF is also equal 4. So because they match, then we would classify this set as a linearly independent set. Next, this theorem is telling us that if we have, okay, so let's remember that these columns here are going to be considered as being part of a rectangular matrix. So, and in general, let's see, this rectangle, this here is referring to a scenario like this. You may appreciate the perfect shape of my rectangle here. So this rectangle has m rows, and then it has n columns, okay? And so when you have this scenario where n exceeds the number of columns exceeds the number of rows, so that's exactly what the matrix would look like. It's a matrix that has more columns than rows. And each of these columns in this matrix, each of these columns is an element of Cm, right? Is an element of Cm. So each of those has m entries. So immediately this establishes that there will be linear dependence for this set of vectors. So if we have a square matrix, we now make a connection, non-singularity. Remember, non-singularity is connected to the homogeneous system that has this matrix as the matrix of coefficients. Okay, and so if the only element of this solution set is the trivial vector, then we would say that that matrix is called non-singular. So the other connection is that the matrix will be non-singular if and only if its columns are linearly independent. Okay, if and only if the columns of the matrix are linearly independent. And so the non-singular matrices are a special type of matrices. Here we will revisit this theorem throughout and we will find that all these things are implying each other. So this theorem is called the non-singular matrix equivalences, because each statement here has the ability to imply all the other ones. So if A is non-singular, A rho reduces to the identity. This is such a useful thing. This is saying that if you have that the RREF of A is I, the identity matrix, if A rho reduces to I, then immediately the only member of the solution set of the homogeneous system, this homogeneous system, the only member is the trivial vector. In other words, the null space contains only the trivial vector, and that means that the matrix is non-singular. So being non-singular, it's if and only if the matrix rho reduces to the identity, and then here are some of the things I was mentioned. The null space contains only the trivial vector, and the columns of the matrix are linearly independent, and a system with a non-trivial vector as the vector of constants is going to have a unique solution for each possible selection of that vector on the right side of the system. So the theorem that we have visited before, let's make a pause here. Okay, we're going to make a pause.